and supporting us always. I'm talking about our Joint Secretary, Honorable Joint Secretary, sir, Shri Vinit Mathur Saab, who is himself an engineer and knows about the technicality. One day we were discussing about this project, time dissemination project, and he was just putting the diagrams about how the satellite works, how the signal comes. So he was explaining us, and the Secretary Saab and all were very happy to know that he is having this much understanding of this. So today we have with us Professor Banerjee, who is a retired scientist from National Physical Laboratory, and he is well-known person in the field of time and its maintenance, its generation, its dissemination in the whole over the world. And fortunately, sir, he is kind enough when I requested him, he is ready to give us some series of these time dissemination project as we are working on this project. I think it will be a very good workshop for us to understand what we have to do, where we are, and how we have to move further, sir. So we have with us Professor Banerjee. Sir, I was talking about Mathur, sir. Mathur, sir is always very helpful. I am always requesting him, sir, help us in this RSL, help us for this RSL. Our people are facing some problem, and he is kind enough, not as a technical, not as an administrator, but as a person, he is so helpful. Everybody would like to. Yesterday, one person met him from, he's actually retired deputy director long back. He met him, and he was saying me yesterday, I have never seen an officer, sir. This is, I'm telling you because you are not aware of that. He came to me at the end of the day, and he told me that I have not seen an officer who is giving this much time to a retired officer. Maybe I think you have spent a lot of time with him. You patiently listen to him what he wants to say. Sir, first of all, before going to start, I would like to request you to kindly inaugurate our workshop on this time project, sir. Please, Mathur, sir. Joint Secretary, sir.
Thank you, Ashutosh ji. Thank you for those kind words. Good morning to all participants. Very good morning, and my greetings to Mr. Banerjee from NPL, who's the expert on the time dissemination and the quality of time and its availability for all our scientific and other commercial work in the country. So, as you would be aware, and many of our participants who are attending, the quantum of time and its correctness is of importance, and every country has to have its own standard time. Although we have something called the Indian Standard Time, but we align that particular standard to the international standards, and possibly till the nanosecond corrections, we get those time from the international satellites through various agencies. Now, in such a situation, sometimes it is felt that largely dependent on the international time standards to give us the national time, and therefore it may not be very useful for us in our scientific and strategic work areas, and it may be required that we should have our own system of timing. If I may just give a small example, which I probably try to understand about this particular issue. If you look into the mobile phones and the digital time which is made available there by different telecommunication companies, and if you compare the two telephones or the mobile phones, you may find a marginal difference of a second or a two in the time which is displayed in these telephones. So every person is carrying an instrument which is getting the source of standard time from a very different probably agency or a standard or a source. So in this country, we possibly want to align this. And therefore, as a strategic decision, the government had decided a few years back that the Department of Consumer Affairs will support this particular issue in relation to the commercial organizations seeking time from the government. And therefore, we have been in the process of setting up atomic clock and time dissemination procedures across the country in our various RRSL time labs. As far as the legal metrology issue concerns, we all understand that length and weight and time, these are the things which we all learn probably in the SI system of units. And the importance of time we slowly come to realize. And it is extremely important that the time should be correct and available. We all probably listen to All India Radio, and we are probably vouching for the All India Radio time. but where exactly the All India Radio is getting that standard is important. And our expert here today is going to speak in depth about how this entire domain functions and what are the nuances and importance of this, and what is the benefit for a common consumer and a person also, for the scientific industry as well as for commercial world and for individuals like us. So with these words, I congratulate Ashutosh also for organizing these knowledge series lectures on a regular basis on very interesting topics which touch upon the lives of every person. We would like to listen to our expert for the day, and with these words, I conclude my remarks. Thank you very much.
Thank you very much, sir. Thank you. You are all your words are always very motivating and tells us how to move further. Thank you very much, sir. We are always looking towards you for better, better appreciation and better helping. Thank you very much, sir. Sir, we have with us today Dr. T. Venkatesh, who is a known person in the field of medical. He's a doctor. He is from St. Joseph College, Bangalore. Sir, Dr. Venkatesh, can you switch on your mic, speaking mic and camera, please? Dr. Venkatesh.
Unmute me. Unmute me. Are you able to hear me, Ashutosh?
Yes, sir. Yes, sir. Yes, sir. We are very well able to hear you.
Thank you.
Please, sir.
Thank you very much.
Sir,
Tell me, repeat your question, please.
sir, I would like to request you to kindly speak to us as you are a known person in the field of medical science. So today we are having the series on this time dissemination. Basically, it's a technical time-related subject. But sir,
Okay.
as I remember, you have done 2-3 workshops with us. Certainly, sir, we would like to have another workshop on these medical laboratories very soon with your kind help.
Sure. I will tell you, we are talking about the time management. Am I right?
Sir. Yes, sir. Please, sir.
I tell you, there is what is called turnaround time. Very important. There's what is called turnaround time. The turnaround time is the time from the time the clinician requests for investigation till the report goes to the clinician.
Okay.
That is called the total turnaround time. It is composed of number of activities. From the time doctor requests for investigation till the phlebotomist or a nurse draws the sample. From the sample drawn till the sample is transported to the laboratory. From the sample received from in the laboratory till it is processed in the laboratory. After that, from the time the result is released from the laboratory till the doctor receives the results. There's a technology now. There are laboratories to reduce turnaround time with pneumatic transportation system or internet transmitting of results. Unfortunately, more than 80% of the laboratories in our country, they have what is called sample transportation from one city to another city. They are maintaining environmental condition. They have a temperature logger, everything is controlled. But the time samples are dispatched from Rameshwaram to Delhi, it reaches after 3 days for some DNA test, and many samples would have undergone some changes. Now, this is some big problem we are facing in this country. Samples are transported from one lab to another lab. It is taking time. By the time the biological sample, which is called a live sample, is undergoing a lot of changes. This is something which we people in the laboratory have to look into this. Number two, the measurement of time. As we are talking about metrology, none of the labs have calibrated their time measurement. They have calibrated temperature, calibrated speed, calibrated volume, but time calibration is not done. Turnaround time is something which is of great significance in deciding the quality of examination results. These are the few words I would like to share with you, Ashutosh, and the listeners of this. Thank you very much.
Thank you very much, sir. You are always, you always throw the light on the new concept, which I actually don't know. Maybe other officers may be aware of that. Sir, we have with us our Dikshit sir. Sir, kindly speak 2 words. VN Dikshit sir, before we going to start. Or otherwise, I'll take later on. Sir, Banerjee sir, you please kindly start.
Okay. So
Please.
let me go to the slide share.
Please, you can share, sir.
Are you able to see?
Yes, sir. We are able to see.
Okay. So first of all, I must thank Mr. Ashutosh, who has given me the opportunity to share my experience in the field of time and frequency, which I am working for the last more than 35 years. So, and before I start, I would like to uh, thanks Mr. Mathur and Dr. Venkatesh for their excellent prelude to my talk. They have nicely highlighted the importance of time in a very simple words. And let me tell you, the seminar deals with basic concept of time, IST, timekeeping, and time distribution. So this whole gamut of subject cannot be covered in one particular session. So I have uh, divided in two parts. The first part I'll emphasize on time and timekeeping, and the another important thing about the time dissemination and distribution, about the calibration, what Dr. Venkatesh is very much concerned about that. I'll cover it in the next talk. And so you'll excuse me that what you are concerned with, I'll not very much go into detail, but I'll definitely touch upon to rather satisfy your curiosity to some extent. And with this, let me start time and timekeeping. Now, time is, let me outline my talk. I have separated in first I'll talk something about concept of time, how measuring is done, and development of timekeeping device, its little history, and advent of atomic clock, and how time is defined. So before starting, there is a different types of participants is there. So I'll start from a very, you'll excuse me for that. I'll start from very elementary things which may be familiar with all of you. So please excuse me. This is important to have a continuity of my talk and bring the point in a nice way. So, so first I would talk about 7 base units, which to some extent Dr. Venkat has also referred to, that in among the 7 basic base units, for example, kilogram for mass, meter for length, second for time, ampere for current, Kelvin is for the temperature, mole for the amount of substance, and candela is for luminosity. So out of that, these 7 units, the time has a different feature. For example, uh, kg, meter, mole, you can see, you can feel it. Temperature uh, and ampere, you have a different way of have a feeling of it. Luminosity, you can have a glow. But time is such a thing that you cannot see it, you cannot touch it, you cannot store it, and time cannot be perceived by any physical senses. Then what is time? The what is time is a really, really baffling situation for the human mind, that it is very elusive nature. You do not know what is it, how to record it, how to regulate its type, and whether it even exists as a fundamentally unit block of the universe. This is really very baffling situations. But one thing is certain, that passing of time denotes the change, and the change like time is inevitable. To have a little concept, I let me go to the Bhagavad Gita in the chapter 11 of verse 32. The what Lord Krishna said to Arjuna, he defined Kalaosmi. He says that time I am. Lokakrita praviddo lokannaso maharmetu hyo praviddo ritopi tvam na bhavishvanti sarve vasista pratinekyosi vodha. It means that Supreme Lord says to Arjuna, I am the time. You need not have to go anywhere. I am the time, destroyer of the worlds, and I have to engage you all people with the exceptions of you that all soldiers on both sides will be slain. This is what the statement given on behalf on the relation to the time. And another important thing is that influence of Bhagavad Gita on the great scientist, the Oppenheimer, who quoted this very verse on July 16, 1945, and who was in charge of the first atom bomb project, and quoted this very verse after the explosion of devastating bomb test, successful bomb test in Hiroshima, and he quoted this very verse. So this philosophical thing is more baffling what time is. But from the very inceptions of civilization, thinkers tried to conceptualize, analyze with very different perceptions. So there is one different school of thought on the uniformity time. There is a different uniform thought how time flows. For example, I give you one simple example that if you go back to the 1687, Newton in his master clock Principia was arguing that even the clock might be imperfect, but real time flows along one direction over the universe, and this is a kind of master clock. And in a very sharp contrast, there is a great scientist, Einstein, in 1905. He given a special theory of relativity where he says that is there cannot be any master clock in the universe. It's a very great contrast to what Newton says. And he says that time depends on the motion of each observer. So the important thing is that uh, that if this two figures you can see that here irrespective of the observer in its internal velocities, the Newton says time remains same, whereas in the in this Newton's idea, sorry, in the Einstein's idea is that it has a different time according to this motion of the observer, which has been depicted in the figure. So there is a two schools of thought. Of course, now everybody has agreed that what Einstein says in the today's measurement is very correct, and it was proved experimentally. I'll come to that in course of time. So about the concept of time, there is another thing is that flow of time. So we all know, we have already concept, it is a belief that the time flows in one direction, in direction from past, present, and future. As the time passes, the moment that was once the present becomes the past. And the part of the future in turn becomes the new present. In this way, the time flows in succession from the present, from the past to present and future. So it goes in a forward direction. But if you go to our religious scriptures, Hinduism, Sikhism, Buddhism, they said it has a cyclic nature. Shatta Yuga, then comes Treta Yuga, then comes Drapar Yuga, then Kali Yuga. It's a cycle of roughly 43 lakhs 20,000 human years, and it repeats. It repeats. For example, there is a birth, and then the death, and the rebirth. So this follows. For example, if you go to that cyclic pattern of Hindu cosmology, so it says that duration of Satta Yuga is 4,800 demigod year. If I assume that one demigod year is the 360 human years or solar years. And Treta Yuga similarly consists of 3,600 demigod year. Dapot Yuga is 2,400 demigod year, and Kali Yuga, which is now we are passing through, is that 1,200 demigod years, which consist of total 12,000 demigods here, which I have already mentioned, equivalent to 43 lakhs 20,000 human years. So again, there is another calendar of Hindu cycle is that they call it cycle of Brahma. According to the Vedic scripture, that cycle of Brahma is that is a period of 10 to the power 22 second. That means it is a 22 second is a huge many years, and it repeats. So the universe, it annihilates and creates. It creates and annihilates. This is a cyclic process, and this is one cyclic process is 10 to the power 22 years. And if you go break up into the little expand it, that cycle and Brahma can have few at different uh, uh, divisions, and you can see that according to the cycle, it goes up to even 10 to the power minus 6 second, that is microsecond. So, so Hindu, this is all plotted in the logarithm scale. So the one cycle is 100 years of Brahma, and one complete day of Brahma is 8.32 trillion of human years. And again, it is a circular. So now, so different perception type we have seen that there is a flow of time, there is a two schools of thought. Even in uniformity time, there is two schools of thought. But fortunately, scientists and thinkers might have differing in philosophies and concept on time. But fortunately, that is important. There is a general consciousness on the measuring principle of time. That how we'll measure it, how we'll show it, how we'll record it, there is a consensus. So there is no difference in the opinion. So that is how we are today, what time is now, what is the status. So I'll come to that. So now before I go into the technical aspect, let me another thing which is again there are three aspects of time. One is physical time. That means what we see in the clock. For example, this is the physical time. Time at present is 10, 11:24. So that is the what physical time is. There is another time is that biological time. It has not strict relation with the physical time, but to some extent it has a relation. That means organism various internal clocks. So we have a heartbeat, we have a breathing cycles, we have a sleep and wake cycles. So these all is a biological phenomena, but it follows a certain pattern. And to some extent, this pattern is controlled by the sunlight available to uh, the human being at that moment. So it's to a great extent it is controlled. For example, when I was in Antarctica for 6 months, when there is a full daytime, so I had a lot of problem in sleeping because we are not used to sleep in the daytime. So that is a that biological time which governs. Another interesting thing is that psychological time, which is a time in human mind when we are very interested, we are in a mind is very excited and we are interested and seeing is that then it is it time flows very fast. But if you are bored and you are the time hangs on you, so the in that case time is compressed or extended. So these are the things I wanted to say in the beginning before I see the technical aspect of time. So the time in the measurement mode, there are three important aspects, which is its frequency, time interval, and epoch. What is frequency? We have been taught in our school days that one is the cycle, repeating cycles. If it has a frequency, that means how many cycles it repeats in 1 second. And T, capital T, is the time period to complete one cycle. This is frequency, and this will be very detailed. I'll talk in course of my time talk. So next is time interval. You see that time interval means time elapsed between the start and the stop of an event. So, so now it means it is something like that. I started my talk 11. I'll complete my talk at 13 hours. So my time interval given is 2 hours. So it is a start of the event, say at T1. and it ends at T2. The difference is your time interval. But please note, this time interval has nothing to do with the capital T, which I have mentioned in the frequency. And the clock is very simple. That what is the time your watch is saying. So this is nothing to do with the capital T also. But the one important thing is that in some fashion it may not be equal to T, but they are some fashions, they are all interrelated. I will come to that in course of my talk. Now, history of timekeeping. This is very important, that how we come to the atomic clock. What is the process evolved in the process? It didn't come overnight that we have got an atomic clock. It is a lot of research, lot of thinking gone through that process. So how do you measure time and how do you get time? These are all you have been you are all aware of it. But one important thing I would like to know, this is the continuity of my explanation so that you can go when I'll talk about the atomic clock. So for time measures, you require a repeatable phenomena. Now you'll have to think of all these things. If you take yourselves to the very primitive age when there was no clock, when there was no time measuring system. So for that time, so they first thought that I'll have to look for the repeatable phenomena. What is in the repeatable phenomena? You'll have to look for the three aspects. What is the basic length of repetition? What I talked about capital T in my previous slide. Basic length of repetition we'll have to know. And beginning of repetitions, when it starts. And another important thing is that this is arbitrary how you name that successive repetition. These are the few things you will have to think of it before people started measurement time. So in the beginning, in the primitive age, people always looked for the natural repeating event, and it was found in the skies. How? For example, they have seen sun rises and set and rises again. So they have seen there is a repetition of the event. So they called it successive sunrise is a duration from one sunrise to the next sunrise. They called it one day. So they have given a name, the one day. So that is the first thing they have observed. That oh, the sun rises and again it rises next day. And it is a very regular happening. So next, they say that month. What is month? They have seen that the phases of the moon changes after a certain interval, and they have called that interval is 1 month. So there is a month. So then it came. Another thing they have observed is that season, that means summer or winter, they repeat after a certain interval of time, and that is a very long interval. They called it that if summer and the next summer comes after a time interval, they called it year. And later it was discovered by the scientist and wise man that it is it is a complete one rotation of the earth around the sun is 1 year. So this is how people started thinking and conceptualists. Now, the another important thing in time is that counting system. The very important thing is that counting system in time is totally different from decimal system what we are used to. The system of time dates back to 2000 BC in Sumer. They made it simple to count with fingers because there was no rather calculator or computer or a any machine which counts the. So their counting system they configured with fingers. So what is that finger they have done it? So they have seen that these pops, the three pops for each finger, they have excluded thumb because thumb they couldn't find a very distinct pops. It's not very common in all hands. So they called it 3, and for fourth finger, it is a 12 number. So they are very convenient with this number. They could manage with the finger. So as because there are 5 fingers, so for each finger there is a so they called it 12. So for each finger they called 12, and 12 is 12 is 12, and that is 60. So they thought that we can easily count 60. So 12 with the pubs, and then for each pub, each finger they have called 12, so it becomes 60. The interesting fact is that 60, division of 60, is still used in time even today after a lot of modernization and sophistication in the electronics and all this. Still we use it. And in angle, we use the also sexagesimal system. And another interesting thing is that even in the coordinate system, latitude and longitude, still we have. So these are the 3 things still followed the sexagesimal system. So now perhaps it was the first only sunlit day. First it was 12, then it was quickly division night plus day was 24. In the ancient Egypt, the 12 hours in each half. Perhaps it was necessary, needed to please their gods. So another important thing is that after ages the hours started to be divided into 60 minutes. And after a very, very long time, the second came because clock was not very accurately available. So the second, that is a division of minute by 60 to get a second, it came very, very late in the 18th century and the beginning of 19th century. People got even a second hand in a clock. Now making a timekeeping device. So I talked about time interval. The time interval is a melting of the, they could see that is a fixed time of a fixed length of the candle with a some same volume. It takes a certain equal amount to melt away. So that is time interval. Again, another thing is that you might have seen in your young days, Leo toy has this sort of hourglass. So it the sand flows from the top full to the all to the bottom, and it takes a certain amount of fixed time depending on the neck width and the granules of the sand. So it takes time. So this is how they used to have a time interval. But the first clock on the nature's oscillation is a sundial clocks. This is the first natural clock devised by a human being. The clock sundial, how it works? It indicates the time of the day, but the position of the shadow on some object when sun ray falls. You see that I can tell you this is called genum. This is Naman is a rod which is inclined at a particular place equal to the horizontal plane, equal to the latitude of the place. So then you will get that if that is the things, then you will get the shadow, and the all the shadow will not of equal length. So the hour lines will not be of equal length. The first Egyptian sundial was found in 1500 BC. The one disadvantage of this clock is that it doesn't work on cloudy days. It doesn't work in the night. Though it was very much used. Even when I was a schoolboy, I used to go to one my friend on Sundays just for um, uh, playing with him, and I was always concerned whether I'll come back to my home in lunchtime properly. So his mother used to tell me time by seeing the shadow in his house. So he said, "Okay, okay, you are not still late. the shadow has not come to that it is not 12 o'clock. So that is how things happens. Now, the Chinese water clock, that was a very, very interesting clock of the mechanical type, where the power is used with the flow of water from a tank high above and used to fall on a scoop to move a wheel. So, water driven escapement clock tower built by Susang in 1090 AD. And it is better than sundial at the still time at night or on cloudy day. So that, but this is a very elaborate and difficult. Oh, Susang took many years to build this clock. But this called is not no longer existing very much in these days, even in the museum, because somebody has taken it out and tried to disassemble, and they could not reassemble it properly. So now the water clock also has a problem that it doesn't work when water freezes. So you'll have to go to a place to work it only where the water never freezes. Now you know that any watch has to work. It requires a power. That was the days even battery was not there. You do not have the power supply. So that's the old days. So they tried to run a clock with a spring power. So that is a spring power. This is in many clocks. It may be also in very old type of clock. You may find it. So spring-loaded clock, and that was used by a very stopwatch in a pocket watch that you might have seen in your grandfather's pocket, and this pocket watch was a very, very difficult mechanical um, uh, marvel. Mechanical, it was organized. So, but thing is that this was accurate 5 to 30 minutes per day. It's a very rather exemplary work. Now, let us come to what Raja Jai Singh, Maharaja Jai Singh, his architectural marvel in the form of sundial and Samrat Jantra. He built 5 observatories all over India, starting from Delhi, Jaipur, Banarasi, Mathura, and Ujjain. I'd like to cite 2 important sundial. So, the one is sundial at Ujjain. The specialty of this sundial is that the Ujjain is at the latitude of Tropic of Cancer. That is, its latitude itself was 23.5 degree, which is same as the uh, tilt of the equatorial plane with respect to the ecliptic plane, which is the plane in which sun moves, the earth moves along its around the sun. So, and another thing is important is that the sundial at Jaipur, it's a very, very accurate sundial because it's so big. So its shadow fall on 2 walls, and the the time is engraved to records the hours, and it is accurate to the fraction of a minute. So it is what's still or is available for the tourist. Now the breakthrough in the mechanical clock is the birth of a pendulum. You see that how it really was conceived by Galileo. When he was only 17-year-old, he attended a mass in Cathedral of Pisa Church, and he had seen that chandelier and inside the church over it was swinging. and there was a breach across the window. What he observed, you see, that what a intuitive idea. He observed the time taken by the chandelier to complete one rotation with his pulse beat, because he didn't have obviously no clock with him. So he checked with his pulse beat. Again, I earlier talked about the biological time. He used his pulse beat, and he was, to his surprise, he found that whether swing is moving fast or slow, it takes equal amount of time to complete one rotation, one swing, complete swing. Whether it is a fast moving or it is a slowly moving, depending on the wind speed of the breeze which is flowing across the open window in the church. So that he worked later on this observation and found that each pendulum has a constant period, and this time could be measured by the swing of the pendulum. So that is how this measurement gave rise to a simple harmonic motion with its time period, which have been taught in our school days. T is equal to twice pi root over L by G. But Galileo couldn't make a clock out of the pendulum oscillation. It was Christian Huygens in 1656 first made a pendulum clock. So the pendulum clock credit goes to Huygens.
संतोष जी कुछ माइक शायद ऑन है, उनको बंद कर दीजिए.
Yes. Okay. Thank you. So few seconds per day is the few seconds per day, or 10 to the power minus 5, is the accuracy of these clocks. Those who have seen the Big Ben in London is a famous clock based on pendulum, and this clock, few seconds per day. An interesting information I would like to share with you is that this clock has a bob of 203 kg, and the length is, the L of this clock is 4.2 meter, having roughly 2 seconds time period, which you can calculate and find it is equal to 2 seconds. You see that pendulum clock serves the time picking for a very, very long time till the quartz was discovered. I'll come to that. This is equation of time. I'll not deal with it. That is the sunrise to sunrise. It changes with season. So, but one important thing I would like to mention about the escapement mechanism. This is a great thing. This is an important thing that made the mechanical clock possible. What is this escapement mechanism? It is a special tooth wheel that advances by one tooth each time the pendulum completes the swing. So this is how it works. So that I thought that I should bring to your knowledge that what is the role of escapement mechanism in the mechanical clock. Now let us talk about, I have given you the history, how the mechanical clock progressed. Now let us talk about the realization clock. Let's try to understand what is inside the clock, how it works. So it consists of few important building blocks, like frequency source, which is nu by 1 by t, and the counting mechanism system, synchronization system, and time display, so it is t. So I can give a simple equation, is that what is this small t is a summation of t, that is, it counts continuously and it counts the number of t and with the initial setting t0. That is called synchronization. It may be 0, it may be 2 nanosecond, it may be 4 nanosecond, anything. So this is a very simple basic phenomena how a clock runs. Now, question comes is that how to improve these clocks. To improve the clocks, let us go to our school days one equation again, that this is a ideal sinusoidal wave, but in practice you will not find such a clean wave anywhere in the world. This is all in the paper. The actual clock looks like this. This is some exaggerated figure, but what I would like to emphasize is that there is a fluctuation in the cycle repetition time and the frequency and also the amplitude. So if I would like to give a mathematical equation, don't I'll not bore you with a mathematical expression, but I'll go little bit, which is very much important to bring my point what I would like to say. So this can be represented by Vt is equal to V0 with some perturbation in the amplitude, and the sine twice pi nu 0 t plus phi t. This is the equation. You also very familiar, whatever may be your or other specialization. So you have been taught in your school days and the later lot of discussions on your college and postgraduate days. The one important thing is that in this equation, what is phase and what is frequency? Now, what is frequency? What is important? The phase is the entire phase is that 2 pi nu 0 plus phi t. But the frequency is not only nu 0, it is nu 0 plus 1 by twice pi d phi dt. I have asked many postgraduate students, given this equation, what is the frequency? Everybody, without a second thought, told this nu 0 is the frequency. But in true sense, it is not. Why? Because total phase is this, and the rate of change of phase is frequency. So when you say nu 0, you are ignoring this part, which is very important in time and frequency uh, field. Now, let us introduce another terminology which you are not very familiar. You are all know phi. You all know nu 0 and pi. But most probably, most of you do not know the term phase time. That means phi by 2 pi nu 0, which is actually phase in terms of time, in the dimension of time, because its dimension is second, because it is radian, and here is also a radian, and this is inverse of second. So radian cancel out, so it becomes second. So why I'm emphasizing on this, that xt, the phase time, is what we measure in the pulses, second pulses, which we compare with another clock second pulses. This is what we measure with the time interval counter. We do not measure phi, because when if we were to measure phi, their unit would be degree or radian. So if we measure pi, difference between two pulses is always in the terms of the second. So then x makes some sense. And the fractional frequency offset, that a dx by dt is 1 by 2 minus 0 d phi dt. This is the fractional frequency offset. That means if you have an offset del f, the del f by f is your fractional frequency offset. I'll come to that in detail little later. But here I would like to emphasize on a very important aspects of the frequency. You all know that what is frequency, how we define frequency? It is number of cycle per second. Or another little advanced definition is that rate of change of phase. So from this very two definition, you can very well imagine Therefore, if you try to measure a frequency, we cannot measure frequency instantaneously because the these two definitions prevent us to measure time instantaneously. Why? Because it always says that you'll have to count the number of cycles over a certain period of time and then divided it by the time you will get the cycle. So you'll have to make a measurement over a certain period of time, then you will get frequency. Similarly, if you see the change, phase change, so phase change, unless you observe it for a certain period, you will not be able to see the phase change, rate of change. So these very definition says frequency cannot be measured instantaneously, but it is a average value over a certain time tau. So I'll refer this tau very frequently in my next type of all discussions. You remember this tau is the averaging period time over which the frequency measurement has been carried out. That will not make the frequency value different because moment you observe for a little longer time, your number of cycles will increase, and if it is observed for a very short time, so number of cycle will decrease. So from this you can very well imagine if your observation time is longer, you may have a little different than the observation time. So because it is a stability what matters. Now this is again, suppose a frequency is yt at a time, which again may change with time. Though I have told you that you cannot measure instantaneous frequency, but if you measure for a 1 to 2 second today, and then after some time, some period of time, you again measure the frequency, that frequency little bit depart from the initial frequency. So I am giving a model of the frequencies that y0 plus ya. That means if it is a drift, you have heard of the crystal drift, aging. So this is the aging factor. So yt is equal to y0 yat. So if this frequency status is this, then if you run a clock with this frequency source, your x will depart from that. This is integration of y0 at dt. Then you will get y0 t del t0, which is the integration constant. Maybe it's the initial phase, and y0 t and half ya t square. So these are the two important equations I will plot. Okay. I would like to bring a very important thing to your knowledge, which is used in your common day-to-day practices. So you see that let us have a y, which is a constant. That means y is equal to 0 and ya is equal to 0. This y0, 0 means it is not a zero frequency. It is a fractional frequency offset. That means from the center frequency, it is little off, and if there is no offset, then it will be 0. So this means it is exactly the reference frequency as the frequency. And ya, that means there is no aging in the frequency. So if that is that, and if you use this in this equation, then it becomes a straight line again as the frequency. So y and x has the same nature, it is constant over the time. And why I've given a double arrow, that means that it depends on this value, it depends on what is the initial setting, del t0. I would like to draw your attention to this particular case. I'll give the other two cases, which is very important and happens in your daily life. When your frequency is little more than the reference frequency, that means reference frequency is here, otherwise it has gone little higher. So, and if for aging, I am saying for the convenience of your understanding, that is 0, there is no aging, then your clock will go like this. the clock time will increase if your y is greater than the reference frequency. That means what is if your frequency, not sorry y, there is an offset, non-zero offset. Similarly, if it is less than the zero, that means your offset is in the negative, then your time will go down. That means, so these are the two cases which you regularly face in your daily life, is your clock is fast and the clock is slow. This fast and slow is not hard these days because of the your most of the clock is GPS driven or a mobile clock, which is much better. So, but I remember in my school days, I used to say my clock is fast than the clock I have seen in my house, a better pendulum clock. You might have heard people saying my clock is slow today. So this is what happens there. But the ideal situation is this. This is the ideal situation. Now, what are the ideal situation condition is that y should be 0. That means there is no frequency offset, and then your time will remain constant, whatever may be the initial phase. So, if you recall these situations, then I would like to see the what clock structure means. It has a frequency source, it has a counting mechanism and synchronization, and the display time that I have already explained. Now, what I have just now discussed, if I come to that, in the ideal case, I'm expecting that yt to be 0, and in another ideal case, x to be 0. Now, in practical situation, y cannot be 0. You cannot have two clock. One is reference, one is you have made it exactly same as the reference. Practically, it is impossible. So, and x also not 0. Important is that if yt is not 0, now people are trying to search that how small yt we can do. Can you make a clock yt as small as possible? That is why you have heard that cesium clock is 10 to the power minus 13. That y is minus 13, 10 to the power minus 13. That means that small it is, y. So there is a continuous effort to make this y as small as possible. And this is the basic research what we are all doing all throughout the years, even today. How to reduce the value of y. So from these discussions, we can say that frequency source, heart of any clock, and regulating mechanism cycles is a regular and periodic way, and the other two parts is the mechanical counting and the arts. So my next all part of the talk will be how to reduce y. Then I'll get a better clock. The accuracy and stability primarily governed by the quality of the base oscillator and periodic process that I explained amply. That I'll have to make it stable and accurate. I'll have to make it y as small as possible. And there has been continuing extensive research on the development of better and better frequency source. Now, what is the status today? Till today in our, now we are trying to have search for better clock. Either you call it a research or it is a search for better clock. Again, what we are trying to say, looking at the frequency. And it is not nu zero would like to make, but y zero would like to make it 0. Nu zero may be anything. Now, the first important discovery in the clock is that after pendulum was very good so far as the mechanical clock is concerned. But the next step was when the electronic system advanced a lot. Then the quartz started playing an important role in clock making. It is an electronic oscillator which we have heard before the quartz, that Colpit RC oscillator. There are so many type of oscillator. Hartley, Colpit, you have been taught in your school days or college days. And they are based on mainly RC or LC. But those clocks could never be better than 10 to the power, that offset, frequency offset, could never be better than 10 to the power 3 or 4, minus 3 or 10 minus. Now again, when it was discovered the effect of piezoelectricity, that was again a breakthrough in the clock mechanism. It was observed in quartz crystal of silicon oxide. Frequency at which crystal oscillator depend on the size and crystal plane in which the quartz is. What electric all you know that if you give a pressure along some axis, it will generate a electric charge, or if it generates electric charge along some axis, it generates high pressure or is here in the crystal. So people start to use a resonance circuit in an electronic oscillator. So this is what the commercially available quartz crystal resonant circuit with two port available. This is used as a component like RC and LC in a circuit, and I'll show you the circuit like this. So these are all quartz crystal. That is what I've shown the picture, the photographs of a quartz crystal. This is something like this, and the basic crystal oscillator is like this. So this is a simple feedback oscillator, and if you use a plain raw crystal oscillator, then you will get an oscillation which is 10 to the power minus 7 or minus 6, which is again 2 order better than normal RC or LC oscillator. And then even people tried to say the crystal oscillator, how you can improve upon it. So they make a temperature compensated TCXO, which improved the rather stability of the oscillator to 1 ppm, from 10 ppm to 1 ppm. And now this is an oven control oscillator, so that it is this crystal frequency is very much dependent on the temperature. So they tried to have a special with this temperature compensated, but that was not even sufficient. So they put the crystal in an oven, heated oven, so that it maintain a constant temperature in the oven, so it becomes more stable. So it is 10 to the power minus 8. Even better crystal now has been found with a very different technique by properly shaping the crystal and improvement in the socket. But by the time it has come in the market, people started having watch using the crystal oscillator. And the crystal oscillator frequency they had chosen is 32768 for the watch or any clock. Because this is 2 to the power 11, 2 to the power 15 hertz, and there are already chips available which can divide it 10 to the power 2 to the power 15. So that makes, if you have this hertz, you will get easily get 1 hertz out of it by have a division of 2 to the power 11. Sorry, 2 to the power 15. So, and this is very popular these days. Even at throwaway prices, you will get the digital watch with the crystal clock. And now people already got a very good crystal oscillator with a very, very high stability, as good as 10 to the power minus 10. And the first quartz clock was built by Warren and Madison Horton at Bell Laboratories way back in 1927. That is the important breakthrough after pendulum clock and the clock technology. So the accuracy went up to, though I quoted here 10 to the minus 7 to minus 8 according to this, but now the commercially available good crystal oscillator can go as good as 10 to the minus 10. I'll talk about it little later. Now, when the quartz was available, people were still trying whether I can have a little better clock. We can reduce the Y little more. So, when the quartz, it has been seen that is dependent on the temperature, to some extent on the pressure, and it has a lot of other variable factors. So we cannot go better than that. So then people looked at the atom. The atomic structure is now well understood by that time. The atom has proton, neutron, and electron. Not all the atom has proton, neutron, but all the atom, even hydrogen has one proton and one electron. So this is they take care of the basic characteristics of electron has a different energy state and whether that can be properly used. So by the atomic theory, it was studied that electron may have transitions between states. They can give off or accept energy in the form of photon when it goes from one state to the other. When it goes from the higher state energy state to lower energy state, it emits photon. And when it goes from the lower energy state to the higher energy state, it can happen when you have excite him with some photon and it absorbs it. These photons constitute an oscillator in a well-defined frequency as given by this equation. That is nu is equal to difference of energy level, that EA minus EB, and divided by Planck constant H. So why people looked at the atomic clock, rather atom, for getting a frequency? Because by that time it was well understood that behavior of the atom is independent of it is such a very invariable properties that it is independent of the temperature where atom is. It is independent of the pressure where atom is. It is independent of the humidity of the place. It is independent of the location of the place, whether it is in Delhi or in Ahmedabad or in Calcutta or in London. The one atom behaves everywhere same. Even there, if you get an energy out of it, frequency out of it, it remains unperturbed. So why not to try to probe into that atom and try to get access to that frequency and utilize it for our purpose? In picture, what you have seen is very simple because people have already made a lot of research to understand what happens inside an atom and what is its property. But we'd like to implement in practice. It's a very, very difficult job. It's not a cakewalk at all. How atom works, atomic clock works? It is a servo loop consisting of, I'm talking about microwave clocks. There are also optical clocks. So for the time being, for your understanding, let us concentrate on microwave clock. That means the clock which operates, that the frequency, that energy I talked about that nu of the atom we are interested with, which emits frequency in the microwave range. Okay. So I'll talk about this why and how not. What is what? So this it works a servo loop where you have a VCXO through which you feed a microwave synthesizer, which roughly generates a frequency equal to the transition frequency of the atom we are interested with, and then use this frequency to interrogate the physics package. I'll talk about the physics a little later. You assume this is a physics package. When this frequency will match with this resonance frequency of the physics package, you'll get maximum output. If you have a maximum output, that means it is used to control the VCXO frequency as good as the physics package frequency. Needn't have to be same value, but it has a as stable as this physics package. So that means this physics package frequency stability will be transferred to this VCXO. The accuracy of this physics package transition frequency will be transferred to the VCXO through this servo loop. So in the microwave frequency under local oscillator, that is VCXO, a quartz crystal oscillator. It has to be quartz crystal oscillator. Normal RC oscillator will not exceed that because it cannot control to that extent, because it is a locking frequency, locking range, and all these things. These are the factors which has to be considered. The quartz oscillator, the frequency normally in the RF range, it cannot work in the microwave range. So typically 10 megahertz, and the frequency synthesizer is phase locked to the local oscillator. So it locks it to the frequency and produce a microwave signal close to the resonance frequency for a particular transitions. So this is how it works. Now what is physics package? The microwave frequency is used to interrogate the collection of the atoms in the physics package. So at the physics package, these physics package, depending on the proper atomic properties of the particular atom, it varies. This physics package for a cesium clock, for the hydrogen mass are all different. The concept is different of this physics package. But the basic principle are same, that you have this microwave frequency will make this frequency as same as then you will get an output. That is the basic principles. So this is how an atomic clock. It's a very, very difficult situation to have a physics package and the combination of the physics and made this hyperloop works. But with a lot of research and a lot of things, people has become very, very successful these days. Birth of an atomic clock. Though the concept was known and people understood how to implement it, but there was a lot of difficulties in implementing it. But the first atomic clock, cesium atomic clock, was demonstrated by Essen and Ring. This is Louis Essen and this Jack Perry. So they first demonstrated the operation of the cesium atomic clock. But what they found that is less accurate than the existing quartz oscillator. But nevertheless, it at least demonstrated the operation of a cesium clock. So it serves to demonstrate the concept that yes, you can have a cesium clock by this concept. Then immediately after that, many scientists around the world started working on this concept, and a new and the cesium clock has improved a lot in course of time. The atomic clock state of the art of the timekeeping are those performance far exceeds the stability, accuracy, and reliability of a crystal oscillator, very good crystal oscillator. This is the status. So, this based on this concept, they have progressed a lot. Okay. So now, so at present we have a three classical atomic clocks. These are all microwaves typically corresponds to hyperpin transitions of the alkali atoms. So this where people were successful in doing in very good clocks with the hydrogen measure, cesium atomic clock, and the rubidium atomic clock. The cesium uh, hydrogen measure works at 1.4 gigahertz, cesium works at 9.2 gigahertz, and rubidium works at 6.8 gigahertz. This is the particular resonance frequency of the atomic transition we are interested with. Now, these three types of clocks is already have a commercial version. You can get it from the purchase from the market, and it's really readily accessible to those who can afford it. Of course, these are very expensive. So, so if you can afford it, you can purchase it. There is no restriction on it. So these are the few photographs of the. This is cesium atomic clock. This is the rubidium atomic clock, which almost came simultaneously with the cesium atomic clock. And the hydrogen measure, the particular the passive active hydrogen measure, which came into the market before the end of this, uh, before the beginning of the current millennium. And these are the three commercial cesium clock. One is cesium clock, one is the hydrogen measure, one is the rubidium clock. And this is around 1997 for cesium fountain, again another version of cesium atomic clock, but a much improved stability and accuracy than this normal cesium clock. It is a cesium fountain, and this could, but this is not commercially available yet now. This is only some 10 laboratories across the world, including NPL at India, has developed this, and it is in operation for the timekeeping. In addition to this, the chip scale atomic clock has come up, which is again a great innovation and a good addition in the timekeeping. This is an atomic clock, came into the market only in 2010. The beauty of this is that this small, very small size, weighing only 35 grams. But it is an atomic clock. Only thing is that the sacrifice you have to make, but we sacrifice in the stability and accuracy to some extent. But it's better than a very good crystal oscillator. Now, I have talked about atomic clock and the quartz crystal oscillator. How to characterize them, and how we'll say, and what measurement we'll do, that one is accurate, one is stable, how you'll assess that. Let me talk a little bit about it. Now, suppose you have made a measurement of frequency, and this is the value of the time level counter. It's a hypothetical case. I'll tell you there are many ifs and buts in this measurement, but to explain you what stability, what accuracy, and what how you'll characterize it. Now, there's the one case. First case is that the frequency is little above the reference frequency, but it is not varying too much. But it is little away from the reference frequency. So that is why we call it, it is stable because it is not varying too much, but not accurate. So in a polar coordinate, so this is your target, but it is away from the target. but it is scattered in a very small way. That means it is high precision but low accuracy. This is another measurement. The measurement which is increasing, the frequency is always increasing. It may be true for the decreasing cases also. It's increasing and with a lot of variation. So this case, you can see that it is not only much away from there, but it is lot of scattered. So this is not stable, not accurate. So there's a low accuracy and low precision. Now, the another case is that your measurement is varying over a reference frequency line. So, and if you project it, that it is around the target, but very scattered. So, as because it is around the target, so it is accurate, but not stable, because it is a variation lot of there. So, this is high accuracy and low precision. So, this is another term used in the case of stability. Now, the ideal situation is that this is the case where the frequency is not away from the central frequency, and this is the case, and this is called stable and accurate. And listen, this is the case where I talked about previously the ideal situation where y is equal to 0, where y is equal to 0. Now, once given this some idea, what do you mean by the accuracy and stability? Let us give it some mathematical way of explaining it. I have talked about this yt and also the xt. This is, you can see, the plot of the y, and x I'll talk about. This is phase, cannot be presented here. Now, what is accuracy? Let us define. We can say this is a systematic bias. Maybe for in this case, you can say this is an average of this value. You can say this average of this value. This can say average of this value from the center frequency. But we cannot say average here in this case. It may be slightly different from the term accuracy. So accuracy is a systematic bias. Maybe this value is accuracy. Now, what is stability? Stability is normally defined by a term Allen variance, and which is mathematically represented by this is your Allen variance. As I told, when you are talking about the frequency, you will have to define the measurement over what period. So this is your tau. And if you make a number of measurements, and this is x, this is this x. So I'll come to that little later, that for frequency measurement, time interval counter, we may use for measuring the frequency with respect to the base of the time interval counter, base frequency. But normally, when you are talking about the high accuracy regime, then you always compare a oscillator phase or frequency with respect to a reference. Otherwise, it doesn't have a meaning. So that reference, this phase is the difference between the reference and the unit under test. So this phase measurement, if we do consecutively for a number of times and all those things, then by doing it, we get a frequency stability. But this all comes in terms of 10 to the power minus x. So now, this is your fractional frequency. In other words, it is del A by f. What do you mean by the 10 to the power minus 7 yt, that fractional frequency? Which means that if you have an offset of 1 Hz in 10 megahertz, then you have a 10 to the power minus 7 offset, because 2 hertz by 10 hertz is 2 to the power 10 to the power minus 7. So what always in the frequency, when you are talking about the high accuracy, high stability, we always give a term 10 to the power minus 12, 10 to the power minus 13, 10 to the power minus 10. So that means that is fractional frequency. So in that case, the advantage of using the fractional frequency term to define how good is your clock is that it is irrespective of what central frequency you are measuring, whether you are measuring at 10 megahertz, you are measuring at 1 megahertz, but your YT will come the same irrespective of the central frequency. Because if you have to 10 to the minus 7 in a 1 megahertz, then its offset will be 0.2 hertz. Not in the case of 1 megahertz, it will not be 2 megahertz, 2 hertz, then it will be 2 into 10 to the minus 6. But to have a 10 to the minus 7 in 1 megahertz, you will have to have a 0.2 hertz. Now, when we talk about the accuracy of 1 part in 10 to the power 13, that is 10 to the power minus 13, when we talk about, this is the very common terminology used in the case of cesium atomic clock. Now, what is 10 to the power 13 second? Is 30,000 years. That means del f by f is equal to del x by t. That means del t is equal to 10 to the power minus 13 second, 3013 years. And then xt, x, del x will be 1 second. So if 1 second by 10 to the power minus 10 to the power 13 second, 1 second by 30,000, 300,000 years, then it can be, in a layman's language, you can say that atomic clock may lose or gain 1 second in 300,000 years. So it is so accurate. So this is a term we many the layman people we explain how accurate is your atomic clock, cesium atomic clock, is that it may lose or gain 1 second in 300,000 years. So that is what I wanted to say. Now, I'll come to that. That I now introduce that Allen variance as a stability, and this is in logarithmic scale. That means it is 10 to the power minus 10, that is 10 to the power minus 11, 10 to the power minus 12. So you can see the depending on the type of quartz and how it is made, the quartz oscillator stability varies in this range. This. Now, rubidium also varies in this range. So it is better than the quartz particularly, and the long-term stability, little longer period of observations. Cesium is better than rubidium, always, even in the short term and the long term. And hydrogen measure is much, much better than that. Now, this is a broad band I have seen. So this is the exact measurement of a different types of atomic clock. This is a real field measurement. I have got a graph for that. For example, chip scale atomic clock. It's stable in the short term, little above or 10 to the power minus 10, but it goes almost little better than 10 to the power 11 in the long term. This is the performance of a cesium atomic clock. Rubidium atomic clock, one order better than the chip scale atomic clock, but its size is much, much smaller than even rubidium clock, and very less power consumption and all these things. Cesium clock is the best, is the clock, I would not say best, is the clock at present used for the definition of the second. I'll come to that little later, but it is have a good short-term stability and the long-term stability than the chip scale atomic clock and rubidium. You see that this is active hydrogen measure. This is much short-term stability, much better than the cesium clock, and long-term stability has not measure, but at a little longer period, the hydrogen measure stability becomes little inferior than the cesium clock in the long run. But cesium fountain, this is not commercially available as I explained. This has a it is only restricted to different laboratories, only 10 in number, 10 to 12 at present, who has developed the cesium fountain in the laboratory. So the cesium fountain at present operating in all operating coils is the best one in the sense that it has a good long-term stability and short-term stability than all the versions of the atomic clock. So the present day the cesium, though before that even commercial cesium clock, has been used to define a second. Now comparison of the clocks. I have given the only the stability, but different other factors. The cheap quartz oscillator, which is used in the wristwatch, I have already shown the photograph of the quartz oscillator clock. In the household clocks, appliances, cell phone, and all these things, this is a very widely used quartz crystal because it is quite cheap and the stability is quite good, 10 to the minus 11. High quality crystal clocks is a little more expensive, $200 to $1,000, and its stability is one order better, 10 to the minus 12, and accuracy is far better than 10 to the minus 6. Now, rubidium clock, another good quality, is 2K to 8K dollar, $8,000, and it has a stability. And as because it is a very good clock, it is used in wireless communication, live equipment, and GNSS. I'll talk about in the next talk what GNSS is and the navigation. Now, cesium clock, you see, I've already highlighted it because you can see the cesium clock 10 to the power minus 12 is accuracy and 10 to the power 13 and 1. The accuracy of the cesium clock is the best. So, as because it is the best stability accuracy, so there is no other clock better than have a better accuracy than 10 to the power minus 13. So, cesium clock has been accepted as a primary standard of keeping time and frequency, not any other clock at present. And even when cesium fountain has been developed, I'm talking about our commercial versions here. Cesium fountain is only restricted to the few laboratories. So they equally serve the purpose of the maintaining the primary seconds and with an accuracy better than 10 to the power 13. It is almost 10 to the power minus 15 or 14. So you can see this is only used for the timekeeping as a primary standard. Now many time scale use hydrogen measure. Reason being that hydrogen measure has a very good short-term stability, 10 to the power minus 15. But accuracy is little bit worse than cesium clock. So it can be once calibrated, it maintains as a good system for timekeeping. Now here, chip scale atomic clock is very important in the same. That is relatively even cheap than these atomic clocks, even cheaper than the high quartz crystal oscillator. But its stability here is see here 10 to the minus 11, 10 to the minus 11. And in addition, it is very, very small size, weighing only 35 gram. So it has a lot of use, and you will in course of time you will find a lot of use when people will get used to the chip scale atomic clock, which came into market only some 20 years back. Now, I have talked about time, but the earliest is time was defined by the solar day, that is rotation of the earth around its own axis. Why it was rejected in course of time? Because Sorry. Because when crystal clock was discovered, it was shown that Earth's rotation rate is variable. Its fluctuation even can be as bad as 10 milliseconds per day. And reasons was also found that large scale movement of water, yearly melting of the snow and the ice in the northern spring, moon raises tides in the ocean causing tidal friction, physical process occurring or within the earth, and the global event like tsunami. It was in Indian earthquake, and also it was sometimes past. It was in Japan also. So this changed the rate of Earth rotation. This is the recent data that how it varies the duration of the day in terms of millisecond. So then people started thinking that can you have a better time scale than the rotation of the Earth around its own axis? The first attempt to adopt standard, more uniform rotating Earth to use orbital motion of the Earth. That means the rotation of the Earth around Sun instead of around its own axis. And the ephemeris second was adopted in 1960 by the CGPM as the fraction of 1 upon 31556.925.9747 of the tropical year for the 1900 January 0 at 12 hours ephemeris time. That was the given definition. Of course, it was implemented with a lot of different other methods, but it was short-lived, this definition. Because in 1967, by the time atomic clock has matured a lot, and it was seen that atomic clock's second duration, if I assume it to be 9192.631.770 period of the radiation corresponds to transition of the two hyperfine levels of the ground state of the cesium 133. It very closely matches with the ephemeris time. So it was about our time. Why? Because ephemeris time to implement and use the practice was very, very difficult. Whereas its stability is much, much better. So that is why in 1967, the second definition was adopted. This is the definition of second.
Sir, you are muted. Sir, kindly unmute yourself. You are muted. I'm sorry, sir. No, we are not able to hear you, sir. I'm sorry, you are muted, sir. Santoshi, can we unmute here from here? Sir, we are not able to hear you. I'm sorry.
Sir, unmute yourself.
I think Santoshi, he is not able to hear us also. What to do, Santoshi?
अभी तो कुछ नहीं कर सकते, उन्हीं को अनम्यूट करना होगा।
भाई कुछ थोड़ा ध्यान वान लगाओ, जो है तुरंत याद आ जाएगा। टाइम का मैटर है। फोन नंबर नहीं है क्या साहब का?
Sir, I'm calling. Banerjee sir, are you able to hear me? Banerjee sir, we are not able to hear you. You are muted. Kindly unmute yourself. No, sir, we are not able to hear you. Sir, I'm able to hear you through the mobile, but not on the. Sir, we are not able to hear you. Yes, sir, we are not able to hear you. Sorry, sir. No. No, sir. Through the mobile, I can hear you, but not through this meeting. Sir, through the mobile, I can hear you, but not through this Webex meeting. Santosh ji, what may be the problem? Yes, we are doing, sir. Santosh ji, can you check?
सर ये म्यूट वाले ऑप्शन पे जाकर के यहाँ से माइक की सेटिंग चेंज करेंगे।
सर आपको सर म्यूट वाले ऑप्शन पे जाके
म्यूट के बराबर में माइक्रोफोन की सेटिंग चेंज करेंगे।
Yes, sir. Yeah, now you have to change the setting.
माइक्रोफोन रियल टेक।
This is, but still we are not able to hear you. Sir, you kindly change.
Hello.
Yeah, now it is okay. Sir. Now it is okay.
Hello.
Yeah, now it is okay, sir.
It's okay?
Yeah, now it is okay, sir. Now it is okay.
Okay. So I'm just going to conclude it very soon.
Okay, please, sir. Sir, kindly take 2-3 slides more behind.
Okay, I'll do that.
Yeah, please, sir. Santoshi, I have already shared you the sir's presentation. If you kindly share.
Okay, sir.
That will be easy. So now, sir, Santosh, sir, don't worry. Santosh sir is sharing your presentation, sir.
Can you hear me?
Yeah, we can hear you, sir.
Yes. Are you able to hear me?
Yes, sir, you are audible.
No,
Santoshji, please share.
Give me 1 minute only.
Okay.
And that should be circulated to all other officers also.
Okay, sir. I will take the permission from the Banerjee sir, and then we will.
Okay.
So from him also I am requesting.
Yes, sir.
At least a copy should be given to me.
Okay, sir. Sorry, Dikshit sir, डायरेक्टर सर आपका वीडियो ऑफ है. Kindly on your video.
वीडियो ऑफ मैंने कर दिया था.
Okay.
Are you able to see?
Yes, yes, yes.
Is it okay?
Yes.
Are you able to see?
Yes, yes, yes.
There was definition of second. From that very point we were discussing.
Yes.
Definition of second.
You go to the
Yeah, from here.
After this, there was the definition of second.
Yes, sir. Now from here.
From here.
That
Okay.
has been derived
So
from CG.
now what I was trying to say is that previously what we did is that rotation of the Earth around its own axis would be the basis of the definition of the second. But next slide, please. But after the next, yes, after the discovery of the quartz cliff, it was shown that the Earth's rotation around its own axis is not constant but has a variable factor. And it was in the study it was found that there are few factors which make it make it to vary because of the large scale movement of the water, yearly melting of the snow and the ice in the northern spring, moon tide, and the physical process occurring within the earth, and also the tsunami which we really encountered recently, once in India, in the Indian Ocean, once in the Japan. So these all was the factor which is causing the earth rotation to vary. And as a result, people were thinking of a better time source. And next, please. And then what it was found in 19 in hello, next please. Next slide. Okay, so then in 1960, CGPM adopted a new definition of the second based on the rotation of the earth, not around its axis, but around the sun. As a result, the fraction of a second was defined at 1 by 31556.925.9747. But this definition didn't have a longer life. Next, please. Next, the second was defined as a 9192631770 periods of the realization of the corresponding radiation corresponding to the transition between hyperpoint level of cesium 133 atom. This isotope was used, and this was very close to the definition of the second based on ephemeris. So now the cesium now available by the many sources, and even the many atomic clocks has been configured for the space qualification, because these days we all talk about GPS and all these things. So the small weight, volume, lower volume, low power consumption, and it should be rather able to withstand the launch operation and all these things. So it has been configured. Next, please. So this is, I can quickly switch, because this is a biggest clock at present available in the world, near the Mecca, and which is governed not only by made by the Swiss, but it is governed by the GPS and cesium clock. Next, please. So these I have already mentioned, that if you would like to compare the frequency or phase, you will have to have a reference standard. So that means in the time interval counter, there is a option to compare two clocks in a time interval mode, or you can measure any one of the clocks in a frequency mode. Again, I told you, I emphasize on the point that moment you go in a frequency mode, you will have to decide the averaging time. It may be there is many options of 1 second, 10 second, 1000 seconds, and so on. Next, please. So, as because we are almost running short of time, so what I'll do, I'll skip few last slides. I will take up in the next series, but I'll just here I will say that how the time progressed along with the along with the different centuries. The first, it was cesium, Chinese clock. Then, and this shows that how the accuracy improved. It is a number of seconds in one day, how much it has to lose or gain. So that means for a long time, till say 17 or 1800, it was 1 second in a per day was the improvement could be made. But after the discovery of quartz crystal oscillator, suddenly the accuracy improved by very higher order. And for example, first quartz crystal oscillator OCXO could see few hundred microseconds per day accuracy, and now even the quartz crystal oscillator and then cesium clock, hydrogen maser, you can have an time maintenance within few picoseconds per day. And optical clocks, which I have not yet talked about, which is really higher order going to promise. So it has a lot of promise. And this whole improvement of the atomic clock is not very old. It is in the last almost 60 or 70 years, this whole improvement you have seen. Next, please. So I'll skip the local time. You come to the last slide, because I'll not have time for the discussions much. So please, next slide, please.
Sir, but we have, as you already consider our request, next after the one Saturday, next to next Saturday, you will be having another workshop, which whatsoever left today, we will continue in the next.
Okay, then instead of 24th, we'll do it on the next Saturday.
Okay, all right, no problem. So next Saturday, you will continue in the same way, because sir, we want to understand.
And I'll conclude there.
Oh, very good, very good. Thank you very much. So next week we will continue in the same way, sir.
Same, but I'll emphasize on the dissemination.
Please, sir. Thank you very much. At 11 o'clock, again next Saturday.
Okay, next Saturday, no problem. What I'll do, then I'll wait for some questions if you have.
Sir.
I'm very happy that Dr. Venkat is kind enough to be present even to now and Dixit Saab. And I'm very delighted to see that they have taken pains to sit over such a long time and listen to my talk. And I'll be very much like to have some questions from them, so that I can try to answer or share my experience in that. Thank you.
I will take questions immediately after. But first of all, I would like to request our director, Sahab, Shri B.N. Dixit, sir, to kindly speak to us.
Excellent presentation.
Thank you, sir. Dixit, sir, will you speak 2 words, sir? Dikshit sir,
Yes.
please.
First, I will thanks Mr. Ashutosh Agarwal, Deputy Director, RSL Ahmedabad, and in charge Director Legal Metrology, to organize this very program very successfully. And by this way, we got the opportunity to hear Dr. Banerjee. Uh, he was one of the experts in India for the time disseminations, and he is product from the NPL, and we are not able to find out such scientists in NPL at present also, when we are in crisis to implement the time dissemination project. So uh, we find very difficulty, and we always need him, and that if such type of knowledge being transferred, our younger generation will get those very things, and while implementing the time dissemination through the atomic clocks, they will get the confidence and they will be in position to implement it. So that's way he is having knowledge and doubts, and it is requested from you that whenever such program is there, please call all the legal metrology officers of central government to join this workshop, so that all the RRSLs where these uh, time dissemination works has to be started, and most of the places the civil and electrical work has been completed, only the atomic clock has to be established, and NPL has taken some time there, but I hope that very soon it will be in position that we are operating the time scale in India also, and then it will be the question of the disseminations and all that type of things. And even that also, in that very position also, Professor Banerjee, uh, the opinions, thoughts, thinkings, experience, everything we require. So we salute him for his knowledge and wisdoms. Lot of thanks uh, to Dr. Banerjee and Dr. Saab, one more Dr. Venu, no? Venu Saab, and Mr. Ashutosh Agarwal. Uh, Everybody who are participating in programs to make the things successful, and we may jointly always uh, give the success to everyone, those who are participating in the program. Thank you.
Thank you very much, sir. Thank you. Thanks for your convert, sir. And certainly, sir, we are always thankful to my great friend, Dr. Venkateshan, who is always with us in supporting us for disseminating this knowledge to the country. Thank you, Banerjee sir. I'd like to thank Dikshit sir.
Excellent. Excellent
Thank you.
presentation. Thank you very much for organizing this.
Thank you, sir. Thank you very much, sir. Thanks a lot.
Thank you.
Venkat, and thank you for the kind words to Mr. Dixit. And I'm always encouraged by you people. And Ashutosh, do you like that there will be some question on the chat or something like that? Or
Sir, next, I think in the next session, after this completing the presentation, we will be having this question answer session.
Ashutosh, is this recorded talk available later?
Sir, it is, but I don't share it to the all participants.
No,
Few
no.
of them, yeah, I
Okay.
can share it with you.
Oh, thank you very much. Thank you.
Thank you, sir. Thanks a lot.
Ashutosh, I'm happy that you have recorded it.
Thank you, sir. Thank you very much.
Thank you.